Welcome to students. So, today we will be looking into measuring chaos, and the quantity that measures chaos is topological entropy. So, before we go into what is the motivation for studying topological entropy, for understanding any mathematical structure, it is very useful if we can attach some kind of numerical value to that structure. So, for example, say we want to study mathematical structures and we are attaching numerical values to it. So, for example, we want to study say vector spaces, and we know that the numerical value attached to it is the dimension. We want to study linear transformations, and we find that the numerical value attached to it, well, we can think of eigenvalues. We want to study groups, and we can attach something called the order of the group. So, we have this numerical values, right, attached to this mathematical structures, and then they give us a lot of information about these mathematical structures. And then these numerical values attached, they not only help us in deciding whether the two structures are similar or the two structures are isomorphic, but they also help us in comparing the two structures. So, such values they serve as invariants. And we would like to study one such invariant attached with a dynamical system. So, how does the story evolve? So, basically the story goes back to Shannon. So, Shannon studied when he was studying the mathematics of communications. So, basically this was the mathematical theory of communications. Way back in 1948. So, he wanted to give some kind of a measure to the information that is stored in a message. So, you want to pass message from one place to the other. So, you are communicating messages, and he wanted to measure what is the amount of information stored in this message. Now, it is very easy to retrieve the complete message if this amount of information in it is very small. So, you can completely retrieve, because there is no basic loss of information that you can get there. But on the other hand, if you have a very complex kind of message which consists of lot of informations, then it becomes very difficult to retrieve the complete, or it may not be possible to retrieve completely all the information that was conveyed. So, even when you look into decoding that part, it becomes a very complex kind of structure to encode or decode. So, he gave this measure, he called this measure as entropy. So, this is what is the birth of entropy. So, he called this measure as entropy, which measures the information content in a message. Now, inspired from this concept of measure of information, which actually Shannon had used for looking into the mathematical theory of communication, Kolmogorov defined an isomorphism invariant. So, inspired by this, Kolmogorov, maybe in 1958, defined an isomorphism invariant for measure preserving transformations on a probability space. So, he defined an isomorphism invariant called, this is measure theoretic entropy or it is called Kolmogorov entropy or it is also called Kolmogorov-Sinai entropy. We actually, so the people important here are Shannon's entropy, Kolmogorov, and what he defined was this measure theoretic entropy. These are the various names by which it is known. Now, we are not going to study measurable dynamics basically in this particular course, but you can as well study say some kind of measure preserving transformations on a probability space. So, you have the set of all Borel sets, you have a Borel algebra, and then you are looking into measure preserving transformations. That means, you are looking into that the transformation preserves the measure right after you apply the transformation. So, when you are looking into that aspect, right, that is one more way of studying dynamics, when again you are looking into only measurable systems, or you are looking into measurable systems where again your transformations need not be continuous, you are only measuring them, how big the set is, how small the set is, etc. That also leads to a very nice theory, and there is a lot of chaos involved there also, but we are not going to, because it is outside the scope of this particular lecture or this particular course, that we get into the measurable content also and try to study that. So, we will not be studying the measurable part, but this is here it needs to be mentioned because the entire concept of topological entropy has its motivation from this measure theoretic one. Now, there are many features that you have seen mixing, right, you see mixing, you see transitivity, right. These all concepts are related, interrelated to what you can see for a measurable system. So, you look into measure theoretic dynamics, so measurable dynamics, and if you look into topological dynamics, there are a lot of aspects which are interrelated. Some of the aspects have been motivated from the measure theoretic one, and then they have been borrowed into the topological case. Some of the aspects have been taken up from the topological case, they have been borrowed to the measure theoretic one. But here definitely this is a very much inspired work from the measure theoretic part. Now, after Kolmogorov defined this entropy, it was almost for a long time in say 65, right. So, topological entropy was defined. So, topological entropy was defined in 1965 by three mathematicians, Adler, Conhem and McAndrew. So, as I said that this was inspired by Kolmogorov entropy. Now, this topological entropy that was defined by Adler and all. So, this was defined for compact spaces. So, you need compact Hausdorff spaces, and this was a kind of definition for compact spaces. Later on, R. Bowen, so let me emphasize Adler, Conham and McAndrew also, and then R. Bowen, he defined in 1971 defined a metric entropy. So, this is not some kind of topological entropy, this definition relies on the metric on the topology that you defined a metric entropy and this is now called Bowen's entropy, and we shall see that these two concepts, these two definitions coincide. So, this is the concept of metric entropy. Basically, both these entropies, whether you take it in Adler's definition or whether you take a Bowen's definition, they are called topological entropy. The benefit is that under certain circumstances, defining one becomes and working with one becomes easier. Under some other kind of conditions, right, defining something, some other part and defining Bowen's and then using that becomes easier. So, but in general this is defined for compact topological spaces, Adler's entropy is defined for compact topological spaces, Bowen's definition goes for in a metric setting. So, of course, when the two things are for compact metric spaces, the two definitions are the same, or they are basically they coincide. So, we will study both these definitions and they form nice, this entropy also forms a nice dynamical invariant. So, if your two dynamical systems are conjugate, then they would have the same entropy. And if we try to look into what is topological entropy, so topological entropy is a positive constant and of course, a dynamical invariant. And why do we study topological entropy? As I already said, that this is something called, which can be termed as a measure of chaos. So, dynamical system is called chaotic if it has positive topological entropy. Now, what we are going to do today is we are going to look into what is the motivation behind this definition, how does this definition come into existence and what could one try to visualize it in a very simple terms, and then we will go back to Adler's definition and Bowen's definition and we will look into some properties of topological entropy. Now, where does this motivation come up from? So, if you look into that in very plain words, you think of a sequence of positive reals. So, let x n be a sequence of positive reals. Now, you have the sequence of positive reals, we are interested in what is the exponential growth rate of this sequence. So, the exponential growth rate of the sequence is defined as, you take the lim sup of log of x n upon n, and you take this lim sup as n tends to infinity. So, this gives for any sequence of reals, this gives the exponential growth rate of the sequence. So, now it is very simple to see that if my sequence xn is bounded, then this exponential growth rate will be 0, right, because then log xn is bounded, but your n is tending to infinity. So, this exponential growth rate is 0. But if you have your xn to be some kind of an exponential, so if you can express your xn in terms of an exponential form. So, for example, if you have a b greater than 1 such that your xn is of the form b to the power n, then your exponential growth rate, right, could be is log of b. If your xn is of the form b to the power n, right, this exponential growth rate happens to be log b. So, we are now going to use this idea of exponential growth rate, but then we are working in a dynamical system. So, what kind of sequences do we deal with? So, for a chaotic system, so for a chaotic dynamical system, one of the underlying characteristics is the different orbits Now, you have already seen that for an interval map, right. Sarkowski's theorem says that if you have an orbit of period 3, you have orbit of all periods, right. So, you have different orbits, and it is basically this multitude of orbits that you have which gives us a very rich structure for the chaotic system. So, we are interested in this rich structure of chaotic system. So, we want to measure this using this different orbits. So, topological entropy is meant to measure a measure of the complexity of the system the system is more complex if it has more distinct orbits. So, the topological entropy is meant to be a measure of the complexity of the system, and what does it measure? It measures the exponential growth rate of the number of distinguishable orbits as time increases. We are not formally defining topological entropy. So, particularly this class, let us assume that the exponential growth rate of the number of distinguishable orbits is our entropy, right. Now, we are interested in knowing what do we mean by distinguishable orbits and what do we mean by distinguishable orbit as time increases. So, how do we distinguish the orbits? let us look into say the full shift. So, consider the system where your sigma is the full 2 shift. Now, what we are interested in, we want to see what do we mean by distinguishing. So, we say that for x y in sigma, right, this we say that x y can be distinguished, the orbits of x and y, or maybe I am just saying x y to be distinguished, x and y are distinguished if say my x naught, that means the middle part is not equal to y naught, right, they are different in the middle part. That means we know that this is a metric space, right. So, the distance between x and y, the sequence is x and y, the distance would be greater than equal to 1. So, we are looking them as apart. So, x and y can be thought of as apart. Now, what do we mean by saying that the orbits can be distinguished? So, we say that for x y in sigma, their orbits can be distinguished if there exists an n in n such that your x n is not equal to y n. Now, what does that mean? The same as saying that your sigma to the power n of x is not equal to sigma to the power n of y. That means, now at the nth stage you can distinguish these two orbits. If x and y are same, right, say maybe something greater than n, right, then we cannot distinguish the orbits, because if they will be having the same orbits up to n steps, right. So, we can distinguish their orbits only if they are basically within that bracket of time that we want to see, within that bracket we are able to distinguish them. So, we say that the orbits can be distinguished at time n, right, if up to n we can get some kind of value k for which sigma k x is not equal to sigma k y, then we can say that we can distinguish them. Now, we know we have studied the full shift, full 2 shift very well, right. So, we know that we can able, since there are two to the power n different blocks, right. So, if you want to know how many distinct n blocks are there, we know that there are 2 to the power n different n blocks, right. So, we are able to distinguish only 2 to the power n different orbits in sigma at time n. So, if we want to look into time n, what happens up to time n, how many orbits can we distinguish? We can distinguish only 2 to the power n orbits. So, what is the growth rate of distinct orbits in sigma? So, the growth rate can be given as, now I can write it as a sequence. What happens at the time n, how many orbits can I distinguish, right. So, this can be given as 2 to the power n, the sequence 2 to the power n, right. So, the growth rate of orbits in sigma, I can write it as a sequence 2 to the power n. And what is the exponential growth rate of this? What would be the exponential growth rate here? Log 2. So, we can say that for the full 2 shift, right, the topological entropy is log 2. Right. As we said, we roughly say that growth rate of these orbits is giving us the topological entropy. So, we can say that the topological entropy of the full 2 shift is log 2. So, let us note it down also. So, the topological entropy let us work with our dynamical system. So, we say that for any dynamical system, if the number of distinguishable orbits at time n is say a function n of n, then the quantity one by n times log n of n, right, can be interpreted as the time average of the complexity of the system during the time interval So, now my time interval is 0 less than t less than n. So, during this time interval we can say that the time average of the complexity is 1 upon n log, and then the Lim soup is n tends to infinity of this quantity. So, this is like 1 by n log of n n. This is a time independent measure of the complexity of the system. And we can take this time independent measure of complexity to be our topological entropy, right. We will formally define topological entropy in the next lectures, but presently we take this to be our topological entropy, and we have seen that for this, for the full 2 shift, right, this time independent measure of complexity happens to be log 2, which is our topological entropy. So, let us take X to be any shift space. So, what we do is let X be any shift space. Now, it is easy to see all these things in terms of shift spaces, and that is why we are looking into the example of shift space. So, let X be any shift space, then the distinct n blocks in X, right. we know that we have defined that to be Bnx. So, now if you want to measure this complexity, right, we just need to take this lim sup as n tends to infinity of 1 by n log of Bnx, right. This gives the measure of complexity. Of this shift space. So, for any shift space, if you know how Bnx is working, how Bnx functions, right, it is very easy to find out what is the measure of this complexity, very easy to find out what is the topological entropy. So, what happens in particular if our x happens to be a subshift of finite type? So, in particular, if x is a subshift of finite type, then we know that there is a matrix A Now, how many symbols are there in X? A depends on that. So, let us assume that A is a k cross k matrix. So, there is a k cross k matrix A such that your X is same as X A. Then we know what is B and X in that case. What is that equal to? We know that from any given vertex I, right, we need to go to a vertex j in n steps, right. From any vertex I to any vertex j, if you travel in n steps, right, that is what is going to give you the number of all such paths, right, that is what is going to give you your words of length n in X, right. So, this we can write it as summation. Now, I am taking this vertices, I am naming the vertices 1 to k. So, taking this summation 1 to k, this again this summation j going from 1 to k, right. I have a to the power n, right, I j. So, I am looking into the I jth entry of a to the power n, and if we sum up all of them, then we know that what we get is all the different blocks, all the distinct blocks, right, of length n in X A. And another thing that you can look into from this very definition is that if I look into what is the m plus n blocks in X A, then we know that the number of m plus n blocks in X A will always be less than or equal to the number of m blocks in X A, right, multiplied by the number of n blocks in X A, right? Because any n block can be extended to an m plus n block, any m block can be extended to an m plus n block, right, and if you multiply the two, right, that will always be some number which is greater than the total number of m plus n blocks. So, we have this. So, what happens is that the number of blocks, they satisfy this subadditive condition here. So, what is the subadditive condition? We can simply say that, hence if we take log of b m plus n of X A, this is less than or equal to log of b m X A, right, plus log of b n X A. So, our blocks, m blocks, right, in the subshift of finite type, they satisfy this particular condition. Now, we will look into a small lemma here, and this lemma is basically from real analysis. I would encourage you to prove this, give a proof of this, though we are not going to consider this proof here, but you can try to prove this. So, if I have a n, right, to be a subadditive sequence, That means, what I have here is a n plus m is less than or equal to a n plus a m. Supposing this satisfies the sequence a n satisfies the subadditive condition, then limit as n tends to infinity, a n upon n exists in the extended real line that means I am looking into R union infinity. So, this limit a n by n, if I take the ratio a n by n, this limit exists. This limit can also be infinite, right, but it will all definitely exist. So, this limit is either a real number or it is infinite. Now, from this lemma, right, we can conclude that limit as n tends to infinity, right, 1 upon n log of b n x a, right, will always exist. So, it could be infinite, we are not sure about that, but we know that this limit would always exist. And since this limit would always exist, we can always define a topological entropy for the subshift of finite type. Now, what exactly does this topological entropy subshift of finite type turn out to be? For that, we again have to go back to linear algebra, but we have to go back and study some more result there. So, again there is a result, there is a very famous result which I am just stating here. We are not going to prove that result, I am just stating the result here. So, the result here is Perron-Frobenius theorem. The Perron-Frobenius theorem what is this Perron-Frobenius theorem? So, let A be an irreducible let A be an irreducible, say K cross K matrix. So, A is an irreducible K cross K matrix, then A has an eigenvalue lambda which is positive and is greater in magnitude than all other eigenvalues that A can have. Also, if I look into this eigenvalue lambda, which is not only positive, but it is greater than magnitude than all other eigenvalues, then this eigenvalue lambda has a corresponding eigenvector v. So, we can say that also an eigenvector v corresponding to the eigenvalue lambda has all positive, all coordinates positive. That means V can be written as, because A is a K cross K matrix, right. So, this vector V would belong to R k, and since this vector V is in Rk, you can think of all these Vi's, right, to be strictly positive. So, V is V1, V2, Vk, where each of this Vk is strictly positive. Now, when we think of this part, right, this such a lambda, right, is called a Perron value. Let us say Perron eigenvalue of A, and such a V is called a Perron vector, right. It is basically eigenvector, we just say that it is a Perron vector of A. So, Perron eigenvalue and Perron vector, right, these two are concepts defined for irreducible matrix A. Now, let us try to look back into, let us try to implement this theorem into our discussion. So, let us go back to our discussion now. So, we look into an application. So, if we again go back to our discussion, we started with a subshift of finite type, and now we are looking into, and we also looked into that if we look into subshift of finite type, right, all the n blocks, permissible n blocks, right, can be given in terms of summation I going from 1 to k, summation j going from 1 to k, right, a to the power n I j. So, let A be reducible now. Let us assume that A is irreducible, and let V be its Perron vector corresponding to the Perron eigenvalue, say lambda. So, V be the Perron vector corresponding to Perron eigenvalue. Now, since we know that V is a Perron vector, right, we know that each of this Vi is positive. So, let us assume two constants m and n such that m is less than or equal to Vi is less than or equal to capital M, right, for all I going from 1 to. Now, let us again go back to this once again and try to see how this fits in, this information helps us in determining this quantity. So, first of all we see that if I take m times summation j going from 1 to k a to the power n I j, this would be less than or equal to summation j going from 1 to k a to the power n I j of V I. But if we try to look into what is this, because A has eigenvalue lambda, right, and V is the corresponding eigenvector, then this would basically turn out to be nothing but summation j going from 1 to this turns out to be nothing but, this is okay, I think this turns out to be my lambda to the power n, right, times V I. We are looking into this factor, this turns out to be lambda to the power n times V I, and this is less than or equal to lambda to the power n times capital M, right, because we know that V I is less than m. So, we find that this holds true and this holds true for each of the I. So, hence we can sum off for each I we have this relation, and hence we can take all these I equal to k. So, we can take all these k equations, right, this k inequalities here, and we can sum them all up. So, we try to sum them all up, and what is that sum turning out to be equal to? So, we can say that m times this summation I going from 1 to k, summation j going from 1 to k a n I j is less than or equal to, now let me not write this term here again, right. I am simply saying that this would be, let me not write this term here, just look into this particular term. So, this is less than or equal to k times lambda to the power n m, and hence what we can say here is, now again let me look into this part, what is summation I going from 1 to k, summation j going from 1 to k a n I j, this is nothing but my permissible blocks of length n. So, if I look into this equation again, I can say that the permissible block of length n, right, in x a is less than or equal to k lambda to the power n m by m. So, this gives an interesting fact here. I am again trying to keep this here because we need to define this part. So, or maybe I just write it down this part again. What we have derived here is that the permissible blocks of length n in x a is less than or equal to k lambda n m by m, and then we can say that limit n tends to infinity. Now, we already know that this limit exists, right. So, limit n tends to infinity 1 by n log of b n x a, this will be less than or equal to limit n tends to infinity 1 by n log of k times lambda to the power n m by m, and we very well know that this would turn out to be nothing but log of lambda. So, our 1 upon n log of b n x a, right, if we take this limit as n tends to infinity, that is some quantity which is less than or equal to log of lambda. But then we can similarly, just as we saw this case, we can similarly see that if I take m times lambda to the power n, right, that is going to be less than or equal to lambda to the power n times V I, right, which I can say that this would be same as summation j going from 1 to n a I j V I, right, and this is going to be less than or equal to capital N times summation j going from 1 to k a I j to the power n, right. So, we know that this, we can look into this inequality, and from this inequality what we would get here is that m by m, right, k times lambda to the power n is less than or equal to b n x a, just repeating the process of the previous case. So, what we get is we get this fact here, and so from here we can say, again we can apply the same part here, we can say that log of lambda, right, happens to be equal to less than or equal to limit n tends to infinity 1 by n log of b n x a. Now, what does that give? That gives that this limit is equal to log of lambda. So, I can say that limit n tends to infinity 1 by n log of b n x a is same as log lambda. And what was your lambda? Your lambda happened to be the Perron eigenvalue of A, and so we can say that the topological entropy of x a, right, the subshift of finite type, is log of lambda, where lambda is the eigenvalue, is the Perron eigenvalue of A. So, the topological entropy now for a subshift of finite type, right, can be thought of as log lambda. Let us now look into some example here. So, we discuss some example here. So, So, let me take x to be equal to x A, where A is the matrix, simple matrix 1 1 1 1 0. You can think of this simple matrix. We know that this is going to give us the golden mean shift. What is the characteristic equation of A? So, the characteristic equation of A happens to be equal to x square minus x minus 1, right, and equating it to 0 gives me the eigenvalues here. So, the eigenvalues here, I get 2 eigenvalues here, right, and these eigenvalues are basically 1 plus or minus root 5 by 2. So, here what we get as the Perron value, the Perron eigenvalue I think of it as lambda to be equal to 1 plus root 5 by 2, and we all know what is 1 plus root 5 by 2, right, that is the golden ratio. It is because of this reason we call this shift to be the golden mean shift, right. So, this is the golden ratio and hence we call it the golden mean shift, right, and now we know that what will be the entropy of the golden mean shift. So, the topological entropy of golden mean shift log of the golden mean, right, and this somehow turns out to be something like 0.482121 something of that sort, right, and very well we know that this is positive. So, we can term this subshift of finite type to be chaotic, right. This subshift of finite type is chaotic because of the other definition that we are taking up, that anything with a positive topological entropy happens to be chaotic. There can be another example that we take up. So, let us take a full shift on k symbols. So, let x be the full shift on k symbols. Now, we very well know that if x is a full shift on k symbols, I can always write it as a subshift of finite type, right, with the underlying matrix being a 1 cross 1 matrix, right, with a single entry k. Now, for this matrix, right, the Perron eigenvalue will always be k, and hence the topological entropy will be is log of k. So, if you have a full shift on say S symbols, right, your topological entropy is log S. In the next class, we will go into the formal definition of topological entropy. We will try to look into some properties of topological entropy, and we will try to see that this concept that we just studied, this was just a discussion that we did, right, it matches with the definition. I hope there is no difficulty, nothing over here.